Okay, so welcome everybody. In this presentation, we show a software that we developed based on machine learning. And this is an eye tracker, a low-cost eye tracker based on a neural network and a PC webcam. We see what is an eye tracker actually, and what is the problem related with normal eye trackers. The motivation behind our experiment, the software, the solution that we implemented, and an accuracy test and a possible test procedure for this application. So first of all, we have different types of normal eye trackers in the market. That is a base eye tracker like this, wearable eye trackers, or even professional eye trackers that can reach thousands of euros of price. And the minimal cost of this is $169. So if we want to extend the technology of eye tracking to any country, especially developing countries, there is a problem related with the minimal cost of it. So the motivation behind this is that we want to use our software to use it with a medical test for the early diagnosis of Alzheimer's disease and autism. And we want to use this software with a simple webcam to eliminate the problem of the cost of the normal eye trackers that is present on the market. So the theory behind this Alzheimer's test, what we want to implement is a test to early detect Alzheimer and autism with eye tracking. So the base behind this is that we want to diagnose the MCI, that is the mild cognitive impairment, that is a mnemonic deficit on the patients. This symptom usually decays into Alzheimer's. So the more early we detect this symptom, the more effective will be the therapy on the patient. This test that already exists based on eye tracking technology starts with a familiarization phase where the patient, the subject, will see some images on the screen. After this, there is the test phase. In the test phase, we have a pair of images in which in one side of the screen, we will have an image that is familiar, that we've already seen in the familiarization phase. While on the other side, we have a completely new image that was not shown before. Perché sono connesso.
Disconnected for a while, so we need to link it again.
Aspetta. Questo è connesso all'internet, no?
Sì, devi entrare in Zoom.
Sono su Zoom. Vedi che vedo.
Okay. Forse la connessione, devi scegliere lo share del video, delle sì.
Presentazione, non so se hai visto. Sì, ho sbagliato presentazione, ma lo stesso. Si vede?
Sì, ok.
Ok.
Okay.
So, in this test phase, an healthy subject will be stimulated from the new image. So we will tend to focus his attention on the newly presented image. While a patient that can have the symptoms of MCI will not prefer any of this image because he will not remember what is seen in during the familiarization phase. So the critical point is that with an eye tracker, we can track where the user is watching and apply the eye tracking to this test in order to detect if he has the MCI symptom or not. A similar problem can be proposed to autism, always with pair of images, though the theory here is a bit different. So basically, a healthy subject has a sort of a gratification system in the brain that usually is different from subject to subject, but the most gratifying thing is common to all of the subjects and is social relationship with other people. And this is the brain of an healthy subject. Though in an autistic subject, this order can be completely randomized or can even not exist at all. Okay. Or not exist at all. So basically, how the same test of pair images can be presented in this case is that if on one side of the screen we present an inanimated object or a non-human living beings, and on the other side, for example, an expressive face, so something that represents social stimulus, an healthy subject will prefer the expressive face, will focus his gaze the most of the time on the expressive face, while a probably autistic patient will not prefer any of these images or will even prefer the inanimated object. So in our experiment, we present this couple of images for a certain amount of time. This could be an example where on a side we have an expressive face and on the other side an inanimated object like a cup of coffee, like in this case. So how our software is implemented. First of all, the software is written in Python and it uses several modules to work. That is OpenCV, that is the module that we use to process images and the webcam images, for example. TensorFlow, that is a module from Google that allow us to create a neural network and train them, and Keras, that is an interface to simplify the use of TensorFlow and other machine learning modules. On top of this, we also have two cascade classificators in XML files that are used to detect where the face of the user is in the frame, and another one for the position of the eyes. That is what we need to train our neural network. This is an example of a procedure of how the experiment could work. First of all, we need to gather here we show just the flow of the program, and then we'll go into the detail of each one. First of all, we need to gather data with the webcam, with the eyes of the patient. Then we need to use this data to train the neural network. Then we can run an accuracy test on the neural network to see if it works. Then we have the visualization test that we've seen before with the pair of images, and then we can analyze the results. Before of any function of the programs that requires the webcam, we have this calibration phase. So here we can see the patient face and an ellipse in the center of the camera. This ellipse will turn green if there is a single face into the frame, if it is facing the webcam, and if it is centered in the camera. So with this, we can check if the patient is correctly positioned in front of the camera. So in the left corner, for example, we have some information. We can see that only one frontal face is detected and that the eyes are correctly detected. In any part of the program, if the patient does not assume this position, the program will go in standby. So we don't lose any data, or we don't acquire any not meaningful data from it. On top of this, we implemented also a module that can monitor the heart rate of the patient through photoplethysmography. So basically, on the variation of the color of a region of the forehead, can monitor the heart rate. In this frame exactly, we show that we compare the results. So it has an estimation of 74 BPMs with a real pulse oximeter. And this will be monitored through all of the experiment to, for example, monitor the stress level of the patient. The data gathering work like this. Then we also have prepared a demo with this. But basically, there is this circle moving in a certain pattern. While we watch the circle, the machine records the position of the circle related with the frame of the eyes in that exact position. And this is the data that we need to train the neural network, basically. So each time we see in that position, our eyes are like that in the image. And we feed the neural network with just that. So just 1 minute of this circle moving is enough to train the neural network in order to detect where are we watching. This is serialized into a file, and then this file is used to train the neural network. This neural network in particular, since it can be used, since the collecting data phase is pretty short, it lasts less than a minute, we can train a new neural network each time we want to analyze a new patient. This grants that we can specialize the neural network on that specific patient without the risk of overfitting data. So for example, we can use a more high number of epochs as an hyperparameter, because if the neural network is specialized in the eyes of that patient, that's okay, because we don't want to generalize it. It is another approach, but for now we saw that the most accuracy approach is the one that we train it with a patient, we test the accuracy, and then we use it for the experiment. And this is serialized in order to file again. So now we show some results of our accuracy test and a possible example of experiment. This is how we test the network. So basically the program spawns a predefined number of points to click into the screen. He knows the coordinates of that point, obviously, and he will compare the coordinates with the answer given from the trained neural network. This is an example of an experiment that we did. In this graph, we have on the y-axis, on the vertical axis, we have the normalized coordinates. So if the coordinate is +1, it is the extreme right of the screen, while the -1, it is the extreme left of the screen, and the 0 is the center of the screen. In the test in particular, it first spawned the axis on the left and then on the right and compare the answers. So here we can see graphically the expected answers, that is the real coordinate of that precise x. In this case, as we can see in the horizontal axis, we tested it on 100 points on the screen. And in the yellow line, the answer for that same point of the neural network. And on the right, we have some data. We can see that the average error it's 3%. We tested it on a 24 standard inch monitor, and that corresponds to 1.6 centimeter of error. That is pretty low. And the most important thing for the experiment that we talked about before is that the ability to distinguish left from the right is of 100%. That is pretty precise for a normal webcam. So an example of test procedure, we will have a configuration file in which the medic, for example, will decide how many pair of images to show. So here we have 4 pairs of images, and for how much time this pair of images will be shown. So we have 4 pair of images of 10 seconds each. This is what the patient will see. And after the experiment, we will have some results, some output that will show how many frames the patient looked at the left, how many frames were not recognized, or the patient was looking at the center or not at the images, and how many frames the patient looked for the right. This is a simplification. The program is a bit more precise in the analysis. We will see that later into the demo. So in this case, for example, if you want to analyze the first pair of images, we can see that the patient focused his attention on the left. If we overlay this, we can see something like this into the end. So that, for example, for the first pair of images, the patient focused his gaze on the left image. In order to make this thing to work into a medical environment, we made an architecture that works with the software with 2 different machines, so connected via network. So one machine is the doctor. That is a more powerful PC that supervises the experiment and do all of the predictions with a neural network. And the other machine that can be a cheap machine is the patient. That can be a normal laptop or an all-in-one PC or even a micro PC like a Raspberry with a webcam and a monitor, because the patient just capture the frames from the camera and send the information to the medic that elaborates them. For example, questo si può chiudere. For example, if the patient is watching during the experiment these two pair of images, the medic can also see in real time where the patient is looking at with a red circle, and also the heart rate of the patient in that time. And we also wrote a paper on this that we're going to present to the next Melecon conference. And next week also we will encounter some medics to decide whether to apply, if we can apply this procedure to a real medical environment. And now we will show a little demo of this. The conference.
Yes, in Palermo in June.
Yes, it's
Next
in
June
Italy,
in
in
Palermo.
Palermo.
Yeah, there is a question from the floor.
Thank you for your presentation. That was about
No, you chop it.
the eye tracking. So, what are the features extracted? Or in your methodology, use a deep learning, not machine learning. The input of the neural network.
The input of the neural network is simply the frame of the eyes with so the image of the eyes, and with this image of the eyes there is the coordinate of the monitor normalized that is connected to these eyes. So when I watch the circle moving in the screen, let's see the circle is in the top left corner, okay? This obviously works only horizontally, not vertically, because for the experiment we need only to distinguish left from the right. So for example, let's say that the circle is at the extreme left, so the coordinate normalized of the circle is -1. So for that frames of eyes, we correspond that -1 as a feature. Then the circle moves, we have -0.9. For that frame of eyes, it's 0.9. And this is the data on with which you feed the neural network.
As a question, are you do some comparison between the EEG to detect Alzheimer and methodology or not?
No, there is no comparison here.
EEG use it to detect and to classify and to predict the Alzheimer's disease. So
we will move on. First of all, we have to start with the clinical validation. After that, we are going to understand how to compare results in medical field.
So now this is just a prototype.
It's from
proposal
from a technical point of view.
We will see this medic and see what they will say to us and how to move on with this. Okay, if there are no any other questions, we will show the demo of the software working.
Please, I have a question.
Yeah,
about the accuracy of the algorithm.
Could you repeat?
The accuracy, okay, it was here. And the accuracy, we have an average error of 3%. So on a 24-inch screen is 1.6 centimeters on average of error.
It's pretty good, pretty good.
Well, the distance between the patient and the
this is the accuracy for the person being autistic, or for the algorithm that's going right?
4 days.
I did not
I
know.
think that this accuracy test is for detecting the eye direction, right?
Yeah, yeah.
Yes,
exactly.
this is where the patient is looking,
Looking at.
into the screen.
Yes. I'm asking about the accuracy of the person being autistic or not, for example. Did you have any results?
Diagnosis.
Mm,
Having diagnosed the hardware.
I did not
No,
understand.
because we didn't. Okay, the point is that from a technical point of view, the prototype is ready, but we have to start the clinical validations. So in order to get this feedback, the answer, we have to test next week, starting from next week. So
Yes,
so-
this is the technical precision, basically.
yeah, exactly. But we didn't start so far the clinical validation, so we have to wait for
This is
Okay,
just
thank
the
you.
absolute precision on the screen of the neural network. So we have the expected result that is known because we decided before we decided to spawn the x in that exact coordinate that is, I don't know, minus 0.7, and maybe the neural network says 0.6, whatever. So that's how the accuracy test was implemented to see how much is accurate on absolute the neural network.
yeah.
In
Just look like the experiment is just for the tracking, not for the communication. So your next step.
Your next.
yeah, right now it is just this prototype that technically works. It is able to distinguish left from the right. We want to see if the medics will approve this for a test with a pair of images. That is the final objective. That is distinguish
And the
how
choice-
much the patient is
exactly.
left on left and on right. So that's the approval that we are looking to find with the
So the
medic.
doctors, they have to decide the couples of images, the sequences of the images, and yeah,
Yes,
exactly,
obviously
exactly.
the entire test procedure still has to be proposed by the medical, and the software will be modified with that.
Technology like this, but to control the mouse pointer for the disabled persons.
Okay, okay, okay.
You can add some intelligent software in the patient side, just to give initial diagnosis, or sometime alarm to the people surrounding the person.
And yes, it's a good idea. Next step. Exactly. We want to investigate this point, but we need to cooperate with the doctors.
What's the size of the training data set? How many people get involved in generation of the images?
Okay, we can use two different approaches. One approach is that we can train the neural network with many people and then use it on another people, for example. This though, we think it is less precise because it has it's obviously less precise because we have more data, we have more different data, so into another person will be more difficult to exactly predict what it looks for, but it is pretty precise, but less than this. This procedure instead, so this test was done on a single person with just a single training. So basically a person sits here, watch the circles for less than a minute, and that data is enough for that patient to see what he's looking for. So by training this with the single patient that is using the experiment, so if you incorporate that in the procedure, obviously we have to talk to the medic to see if that's possible in a real environment or not. We can specialize the neural network more with more epochs, with more reading the data, and we obtain precise result because actually the circle cover any case that we need, and if the neural network is specialized on that eyes and on those coordinates, it's much more precise with a higher number of epochs. So the best way to do it, we think, is that train a new neural network for each different patient.
you have the chance to test it when the lights are kind of low or the lights are high, or you test them in the same condition, right? Lighting condition.
Since the training is made every time, the neural network will be specialized on those particular conditions. But basically, for example, a lamp like that could be used to enlight the patient and have that kind of brightness.
How many points did you select for the neural network to make the instant prediction? Five what's best points? How many points?
This experiment was made on 100 points.
100.
No. I mean at each prediction time, how many previous points you take in consideration? Now, for example,
In the training.
in the, after 5 clicks, how many more clicks did you select in your program to make that prediction?
No, this is each prediction is a standalone. So basically, we take a single frame.
It's not a time series.
Not that
Yes, it's not exactly. It's not a time series. It's on each frame where the patient is looking at. So we
Exactly.
use the single frame as unit.
The system with the same person who trained.
Yes, this is the test with a single session of training and the same condition, patient, and whatever tested with him.
Control the distance between face and screen. We hold the head of the patient.
The calibration basically gives us this thing, basically gives us a decent distance.
The green thing, this is the green rectangle.
That's for the heart rate. The green reticle is for detect the heart rate. It's not related with the eye tracker. The green ellipse instead is static, so we have to put our face inside that, so we have a decent distance. By the way, the distance as far as we see the eyes of the patient, the distance is not important, because if we train the neural network at that distance, we use the same distance for the experiment, and we know that the answer will be the same. So, okay, probably if I go up there, I will not see the eyes anymore. But if I'm at a reasonable distance from the screen, I train the neural network with that distance. I do the experiment with the same distance, and the answer is granted to be the same.
The training is
The distance. It's good. I think it works. It still works, but it will be more precise if the distance is the same distance used in the training.
the training is very fast, so we assume that the distance is the same.
Can you just explain the architecture of the neural network? Use a deep architecture.
Yeah. Now we will show a demo picture.
At the end, you use Raspberry Pi to upload your algorithm.
I don't know.
At the end, for the hardware part, you use Raspberry Pi to upload.
Yes, we will show first each of the single function to train and test the neural network here. For a matter of so in Zoom they can see that since the monitor is here.
And
Then we will use this
Raspberry.
machine as the medic, as the doctor, and that machine as patient. That is a Raspberry. Okay. That's a Raspberry with a monitor and a webcam. Okay. Okay. Yes, it goes. We tested it with the Raspberry, and it goes at 70 Hertz, something like that. The procedure is a bit more sophisticated than that. I will show that later. So first of all, I will show. So this is still a bit rudimentary. So for example, when I want to collect the data from the user, okay. There is a problem because Zoom is using my camera, so I need to disable that. Okay. Obviously, the program needs the webcam. So for example, here you can see my face. Now the light is not so good, so it turns red. So maybe we can use the lamp.
There is another one. Good. Thank you.
Okay, now it is a bit better. Obviously, in a real environment will be better than this. But here we can lock the region on the forward to estimate the heart rate. That is not the important thing of the thing. Now we can see that one face is detected, that is mine, and my eyes are correctly detected, so I can go on. And you can see that I can see this circle moving all around the screen. For example, if I close my eyes, you can see that the circle will stop because it won't recognize me, or if I turn my head, you can see that it stops and it will start again when I assume again a correct position. Once this is done, I also skip through that. We can use this data to train a neural network and test the accuracy. For example, this is the accuracy test. So if I do this, for example, on 10 points, again, there is some problem with the webcam. No, sta prendendo, no. The calibration phase will start again. And I will click. C'è proprio il problema con la luce. Okay. Here they spawn on the left, then on the right. This is obviously a stupid test with just an axis to make it. Okay, it is buggy because when you need things to work, they don't work. But basically, the output is this one. We fixed the bugs, obviously, because it's still a prototype. This is the output after the test, okay? So we will have the average error or whatever, and we can decide if we want to run the data collection again, or if the results are satisfying and proceed with the experiment. Now, we will try this with the real environment. So this laptop and that Raspberry are connected in the same network. So we will try the remote experiment. So we obviously set up.
Non parte. Okay.
Okay, so now they're connected, and you can see that the doctor has the complete control of the experiment. Now it's a bit slow, but just because it's on Zoom. But if you see that from the laptop, it is moved.
Ok, quando sei fermo.
And it can decide when to proceed with the experiment.
Vado?
Now we set up the experiment to show two pairs of images for 10 seconds each. And the interesting thing that you can see, right, is the real-time prediction on the screen. Now I'm looking at the left, now I'm looking at the right, and in real time the medic will see what I'm looking at. I'm looking at the right, left. After this, those predictions in real time are not the entire set of predictions. It's just a bunch of them to not overload too much network. But after this, you can see there it is frozen, but not actually frozen. Now the Raspberry is sending the entire recorded video to the medic. And once this transfer is finished, the medic will go through the entire video again, and for each frame, it will output a prediction. Transfer everything. Okay, another error. Fantastic. We tried it before it was working, but fortunately, we tried it before, so we can show
5 minutes.
this debugging. Okay, we did one before, so you can see the timestamp that is today, an hour ago, because we tested it. And basically, here we can select the two pairs that we've seen during the experiment. These are all of the prediction on each frame. So we can see that in 10 seconds, the Raspberry recorded more or less 600 frames. For the first pair, the patient watched it left for 500 frames. 28 were not recognized or was looking at the center, and 103 at the right. And with this slider, we can go through any single frame, and with this blue bar, see how much it was looking to left and how much on right it was looking at. The same thing can be done on the second pair. So basically, this is the prototype, and this is an example of how the experiment will work on medical environment. Obviously, this is still a prototype. You've seen that it doesn't work perfectly yet, but the precision was working, and the test was done on a real PC with a real environment. And we are obviously waiting for the medical approval to decide what a standard procedure that can be used with this. So basically, the entire point of this is that instead of using
we are using a very cheap solution.
Okay, we're using a cheaper solution instead of spend a lot of money on the specific hardware. So basically, we still have the laptop with the webcam, and using the neural network, we can predict where the user is looking with just 1 minute training, basically. So that's it.
The question is about the neural network architecture you use. Have you used the pre-trained models, deep learning models?
Okay, this is a dense neural network used with TensorFlow with the hyperparameters set manually. So the layers, the number of neurons, the epochs are all decided manually. A nice improvement that I think about making that we want to make later is to use instead some softwares, for example, Keras module after these things to do automatic hyperparameter tuning by interacting with the accuracy test and something like that. So instead of manually set up the entire neural network that gave us that precision of 3% error, we might want to next use automatic hyperparameter to see if we can improve the structure of the neural network. but basically the network is created by scratch. It's not pre-trained. While instead to recognize the face and the frame of the eyes to feed the neural network with data, these are done with predefined cascade detectors, R-cascade detectors.
So it's feed forward neural network, not a deep one. But it's running, and I mean, and Raspberry Pi, I assume that it's like a feed forward neural network would be without like any like 2-layer or 3-layer, right?
Since the Raspberry is not powerful enough to run TensorFlow, basically the patient machine doesn't make any prediction with the neural network. So the Raspberry just records the frames. Then, as you've seen at the end of the experiments, all of the recorded frames are sent to the medic. So basically, even the real-time prediction is done by the medic with an UDP stream, and then he sees the prediction. And at the end, with TCP instead, we send the entire video recorded by Raspberry, and again, the powerful machine, let's call it, will make all of the predictions and analyze the data. So basically, that's just a slave that is recording with the webcam, everything, and all of the computation is moved onto the medic machine.
Okay, the other thing is about the pixel per meter, the ppm you calculated. And how did you calculate the ppm without knowing the distance between the face of the patient and the camera? How you know the ppm, the pixel per meter? How you compare the number of pixels to distance without knowing the distance between the camera and the I see in the screen, you can calculate the ppm while
okay, it's actually it's not
It's
something
not really.
that is measured from that. So basically, the thing is, at the distance, if my eyes looks like this and the circle is in the left corner, it takes the eyes, it says, okay, those eyes, that image of eyes represents that position on the screen. So obviously, if you move further from the screen, this will be a less more precise because the image will tend to be similar to each one. So if you're basically the advantage of being closer to the screen is that you have an higher resolution picture of the eyes.
You haven't mentioned anything about how do you detect the area of the eyes? You cut, right? You cut
Okay,
OpenCV.
that is
OpenCV.
done by those R-cascade classifiers that are not developed by us, but they are open source R-cascade classifiers based on edge detections algorithms. So
OpenCV.
that's from OpenCV. I think they're the same things from OpenCV. You load these classifiers, they detect the face and the position of the eyes. So, and our neural network takes those frames of the eyes and use them to feed.
the whole frame of the eyes. Yeah.
Yes, both frames of the eyes are cut.
The frames, you mean the area, just the area of the.
Yes, just the area of the eyes.
The area on the area.
Exactly.
Neural networks in order to detect.
It is not feed.
Another that selects eyes and another that estimates the gaze.
It is not feed with the entire face. It is feed with the eye frame.
But you have not used the gaze tracker, which is already available in such libraries like OpenCV and the face recognition.
No, the part of algorithm that detect the direction of the eyes is our neural network trained with TensorFlow. So basically, the predefined things that exist already are the tools that we use to detect the frontal face, to detect where the eyes are, and then when we make the data collection session, we take those frames with the normalized coordinates of the point on the screen and feed the neural network with this data. So the neural network is just a frame of the eyes and position on the screen. How we obtain the frame of the eyes is with the edge detection classifier that is already existing. So the thing that we created is the prediction of the look on the screen.
Okay. Okay. Thank you.
Thank you.
Thank you.
If there are no other questions, that's it.
Just pause it.
Thank you. Got it. Can I share my screen? You think I can share the screen? No, I cannot share the screen at the moment.
No, this. What's the? Okay.
Okay. The audio is okay.
What's
So
the account name?
the account name should be AC, this one.
I see this one. Okay. So,
Yes, this one. Which one is co-host? Yeah, Heather. Will be co-organizer.
Rindy, this all. See. Okay.
I'm co-host.
Yeah, you can share.
I can share. Let me try. Oh, wonderful. I share the whole desktop because I think it's better. So you should be seeing my desktop now. Okay, let me close this one because it's all right. So good. So exit. Let me start from the very beginning and exit then. Okay, right. So everybody can see my screen correctly? I'm okay. Do you think we can start? Okay. Hello. Hello, everyone. My name is Alberto Cabri. I'm here to present some demos, some applications that we've been developing in the latest few months. So I think I can take off my mask if you don't mind. Okay. The first thing I'm going to show you is the demo for real-time object detection based on a very small architecture, a very powerful but small architecture, which is the Jetson Nano, the NVIDIA Jetson Nano. This tool works in real time, and it has been, well, let's say it works in remote because at the moment the Jetson is configured as a headless computer. There's no keyboard, there's no mouse, there's no monitor. It's only connected via the network. And I am connecting remotely from my computer, my PC. So I remote, in remote, we have all the graphical primitives. Everything is transmitted over the network. So first of all, what I'm doing is I connect from this PC to the Jetson Nano by using this okay, the IP address is the IP address of the Jetson, and the X option is in order to get the user interface on my remote host. So in this case, I'm using the secure shell and the password. Okay, now I'm connecting. Now I'm definitely working on the Jetson. So first thing I'm doing is I run a Docker container, which I prepared because everything, okay, Jetson is is a very good tool, but it has a lot of dependencies in case you install in its own environment. So in order to get rid of those dependencies and to have an easier setup, I chose to use Docker and in order to virtualize the environment, and so that the environment is closed, is, let's say, enclosed in this Docker, and that there is no impact on the outside operating system. So first of all, I'm running the Docker container. The Docker container is run by a complex command. So let me change the folder. This is the salting folder, and the command cat dot slash run doc. You see, this is a very long command. You need to type all this stuff. So I created a script because it's too long. You cannot remember. There's a lot of flags you need to turn on. There's a lot of complex stuff. But first of all, we start by using this. So just type run docs, okay, and it starts my container. The container is started, and I'm working as a root inside the container, so I have all the privileges. And it's also persisted in, there's a folder which is persisted from outside to the inside. So if I need to change, to exchange some piece of code, some programs I want to make changes, I can do whatever I want and make sure that everything doesn't get lost. Because when you close the container, when you shut down the container, what is done is lost. What is done inside the container, unless you persist it some way with a two-way connection on the host computer. So this is the first thing to bear in mind when you work with this kind of virtualization. And then what I'm doing is now I need to start the application. In this case, the application, it's easy to start because everything has been set up. I have a Python application that reads from the camera in real time and makes inference by using a deep neural network, a convolutional neural network, which is based on YOLO. YOLO is you only look once. Yes, sorry?
Which type of YOLO?
YOLO 5. It's been a bit of work to make it work on this tiny architecture, because it was definitely designed to work on a much powerful architecture. In my case, yes, YOLO 5 is the latest, and it was the best because it works with images of 64 by 64 pixels. 640, not 64, 640 by 640, because the other ones are working on smaller pictures, and so you lose quality. It took me a bit to train the network because I made the first, I had to tag some images to make training, and I basically did a transfer learning, starting from a partially trained network to my own custom data set. And in this case, the custom data set is a data set that has been designed to recognize the components on this board. Only few components, not everything, but integrated circuits, resistors, capacitors, coils, and I think it's done, and nothing else. Yes, no more than 5 objects, but it's just because it's a proof of concept. And so I wanted to make it work in this small test. So in this case, we type Python and then the name of the tool. It takes a bit to set it up because, as I said, it's really small architecture. But if everything works as expected, our camera works at a frame rate of 21 frames per second, the camera. Whereas my tool can work in order 2-3 frames per second. Yes, that's because we have how do you say, a high quality camera. It's 6 megapixel, I think, the camera, so it's very huge image, and we need to scale images in order to make inference. Inference is done on the CUDA, so it's transferred on the GPUs, whereas in order to make it work in this way, I had to use multi-threading. There's another version that I applied with async IO. Yes, if you move you see that it tracks down. And yes, it's a bit slow because and there are some mistakes, because if you see, the coils are sometimes not recognized. In this case, for him, it is a capacitor, but it is not. Yeah. It is definitely a coil, but there are some problems also because the training has been performed only on 27 images. If if we do the same with the more images, I think that we can achieve a better performance. In this case, only 27 images, it's really definitely a good result, in my opinion.
15 labels every image.
Sorry?
How many labels in each image of the 27? I mean, how many objects?
Oh, depends, because depends on the target images, but yes, because when you do the training, you need to set up your data set, and for each of the images, you tag the components that you can identify. So you manually do that. That's why I only chose 27 images, because it took a long time to prepare the data set. So you need to prepare the data set. You need to prepare the data set. You need to tag the images and to select all the components that you can recognize. And some of the components are maybe occluded, some are easy to understand. So you need to give hints also to the training tool. And then after that, you can perform the training.
Excuse me.
Yes.
Are you using that camera?
No, I'm using,
I suggest for you to use that camera. So
because
you
I'm
can-
not connected to
No,
that
it's
one.
not.
I'm using this one.
You should select the
On this one.
the camera that is in the, so the people from Teams can see the setup.
Yes. Okay, let me see, because I cannot.
So you can choose the camera.
Yeah, I hope I can see the camera. I'm trying to.
This is
No, I've already selected this one. It's set on UVC capture device.
so it should work.
Yes, it should work, but I cannot see the view. I cannot see the.
It's not that open.
I don't see what.
This one camera on.
Camera is off. That's why I cannot see the camera. That's good.
Now.
Takes a while. Sorry, I thought it was already.
It is starting.
Yes, I thought it was
So in
already
this
switched
way they
on.
could see the setup.
Yes.
No, from Teams it's possible. They could see what happens.
Yeah, now, okay, so let me preset on.
Maybe I can explain the rationale of this application. So the objective of this research is to extract tantalum, beryllium from the electronic components. Normally the electronics boards going to the West are grown and they operate the chemical extraction from this ground. But in this way, they cannot extract those special materials or chemical components of value. Okay. So if we select extract, we sort the different kind of components, for example, electronic capacitors only, the mechanical and chemical process will be more efficient. So, so at the beginning with the all mix, we don't extract nothing. But if even if we have some errors in the classification, the quantity of electronic capacitor is higher, and so we have more chances to extract the tantalum, for example. Because this is the rationale of this one.
Yes, I forgot to explain the rationale that was behind this solution. Okay, this is how it works. Just in terms of training time, this is interesting because it took me, well, a bit to set up the environment. But the longest time was on training, on preparing the data set, because training, I tried to train my network on the tiny computer, on the Jetson. Well, for epoch 0, it took more than 1.5 days. only for epoch 0. Then I stopped it and it didn't finish yet. It wasn't finished. So I moved on a server, on a real server with a higher computational power, and it took me 10, 15 minutes to perform 300 epochs. So for what regards to the training, you need to work on a powerful machine. For what regards to inference, you can transfer everything here. As I said, I tried a different solution. This is the multi-threaded version. There's another one because recently there's more, let's say, push towards having an async.io based solution. Async.io is a new library that has been developed recently on Python that performs asynchronous input-output without using multi-threading. And multi-threading. Yes, and it works more or less the same. The performance are the same. I have both the versions. I tried both the versions. I also tried to combine the two solutions, but without any invaluable increase. I think that in this case, it's good that we have 2 frames per second. The same architecture moved to a powerful server, to a powerful machine, can achieve up to 30, 60 frames per second. So it is really, the solution in terms of the application, it's good. And the computational power is limited, so we need to do what is possible, okay? But in this case, we could do that. And I think that there's maybe some good space for improvement because the things that I'm trying to do is to get rid of the Docker container and check and see if without the container, it's possible to achieve a higher performance. I do not expect it to go any faster. So, well, much faster, but maybe some 2-3 frames more, it is possible. This depends on the complexity also of the things, how many classes. I think it's all a combination of factors. So this is the first part of the things that I wanted to show you today. Have you got any questions about this in addition to? Yes.
Is there any need for calibration, like the distance to the board?
No, in this moment, there is no need because when I perform the training, I use images that have different distances also, different resolution. And you see that, well, in my office, it was closer. Here it's, well, a bit, you see that it can detect also if you put it a little, yes, it still recognizes the components. Yes, because also because the camera doesn't suffer too much with focusing about distance. So, well, the distance doesn't matter too much. So yes, it's better to have a good lighting and to be closer enough for a good resolution, and also to see what how many components you want to check. I think that in an industrial environment, you should have a camera that can spot the whole board. Yes, this is the main task because we wanted to identify the position of the components in order to maybe perform a selective dismounting. So we can select the components that we want to remove and collect only those from which we can recover more of tantalum, more of something, some other components that are valuable components for us.
Since, as you said, this industrial environment, the distance would be fixed.
Yes, definitely.
You have the images, the training, that's the same distance as all this.
Absolutely. I definitely agree with you. This is experimental part, but when you have a working environment, well, a full working environment, you definitely can do the training, also the data acquisition. It's targeted on the real environment, so you can have a fixed distance, you can have maybe a better camera, because in this case, and also a more powerful detector. Well, we wanted to check what was the performance on this kind of small and cheap computer because it doesn't cost too much. So we can achieve a good result, we can achieve a good performance, but in case we want to improve, there are maybe more powerful industrial computers with reasonable price. So
people in the field, they use the MAC, which is the mean average precision, for as a performance metric for that precision. Because I think here the accuracy is much, I mean, more important than the frame per second, which is the speed of the model. I have some suggestions for you. You can use like the new board of the NVIDIA, the Xavier.
yes, we have it, but I have no time. I had no time to spend on this new board because it's different.
Yes.
So you need to learn everything again because.
The other thing is to use, because YOLO 5 is based, it's written, I mean, built by PyTorch.
Yeah.
And NVIDIA, they have their own TensorRT.
Exactly.
TensorRT.
This is based on TensorRT.
This is based on TensorRT.
Yes, definitely.
Because it's faster, because it's built to optimize.
Yes, and inference is moved complex. The complexity of the inference is moved totally on GPUs.
Yeah.
And there's also an option that I tried that allows us to work in half precision. So you can try to kind of speed up the computation, because if you divide the precision by 2, maybe I think I thought it should have been faster, but it was not. The performance is more or less the same because everything is done in the GPU, and the real bottleneck here is the throughput from camera. You achieve data from the camera much slower than you can perform detection. So the problem is combining both of the things.
The frame per second from the camera is 20, which is faster than the model itself, which is 1 as we see.
Yes, exactly. But the transfer rate from the camera to the computer, the Jetson is low. And when you, well, in this case, I'm using a kind of a shared memory. I must say it's kind of a shared memory, because what I do is anytime I have a new frame available, I put it in a variable, and this variable is my engine. So if a new variable, a new frame is available, the engine uses this new frame. So anytime we complete the loop, there's a new frame, and if the frame is the same as before, we use the same. If it has changed, we use the new one. But it's really, there's a lot of work to do to speed it up, but definitely using Xavier, it's a good option. We have bought one, and it's still in the box because we had no time, but it's next things to do is this one.
How much is your training data set? How much?
The training set.
Is your, yes.
The training set was 27 images, 20 for training, 7 for tests. And yeah, the accuracy. Well, I'm not
the board, the image of board.
Of boards, yes, of the components.
Instead, the pattern, the components are
more, yes, because the components are more or less 5 to 10 components for each of the boards. Yes.
Desire the number of components.
Yes,
So
definitely.
the target are higher than
27 images, I mean that we are working on 27 boards.
Yeah.
On the shape, no, the recognition is not based, well, it's based on a convolutional neural network that extracts the kind of, yeah, you know how it works. I don't have to explain.
Set of features
Yes, the set of features is that for YOLO.
Not everybody knows what YOLO is.
Ah, sorry. YOLO is a convolutional neural network architecture that can perform object recognition by kind of filtering the image and extracting.
This is bad, so you only look once.
Yes, you only.
Because previously you have many, like in the pipeline, many stages.
Yes, each of the stage reduces the complexity.
Yes, because in object detection, you have to detect the object and you have to classify the object and localize the object. So
yeah, I think you end up with more than 128 features for each of the object, and outputs you can detect a class, because each of the features that you extract are small, are selective, and combining those features you can.
it has a backbone and a neck and a head.
Yeah.
It is mainly 3 parts of the even neural network.
It's complex, but it's interesting. I've also used the SSD, single shot detector, and yes, it's faster. No, SSD is faster in this case with I don't know why, but on Jetson is faster. Well, I was working on YOLO, so my last version was on YOLO, and I left that. But I think that if I need to achieve a better performance, something that I want to do is to step back to SSD, because in the first test I did, it was faster.
Because the image was the function or the tool that before the detection and
yeah.
Here we have 2 types of capacitors.
Yes. We have 2 different labels. The electrolytic capacitors, but we have also simple capacitors, and you can specialize different types of capacitors if you want. In this case, because there are a lot of SMD components, it is also difficult to detect to tell resistors and capacitors apart, because SMD are more or less the same. Whether it is a capacitor or it is a resistor, they look the same. So if you want to tell them apart, you need to have boards in which the shape kind of the features are different. So in this case, it's easy to detect the electrolytics, it's easy to detect the chips, the integrated circuits. And you see that it also detects different types of circuits, because this one is pretty much different from those 2 on the right or those which are SMD. So the training is good enough to understand. I think that the worst case of detection here is on coils. Probably because my sample was not good enough for training.
Biased data.
Yes, definitely.
Conductors in the data. And 27, honestly, is not enough at all for this model.
Yes.
Yeah, you can augment your data. You can use the set 27. And
there are tools for data augmentation. As we said before, the hardest part is the training. We need to prepare a very good data set and to work with an extensive data set in order to have good quality of recognition. I didn't also estimate the accuracy here. You see that every component has its own probability. Aside, you can see it as a label in which you see here, this is a capacitor with 82% probability. So just to give an estimate, but as long as this has to become an industrial application, we need to do some additional work.
So here you are only interested in ICs and capacitors.
In this case, I'm interested in ICs, capacitors, electrolytic capacitors, resistors, and coils.
But resistors are very small.
Yes, and they are not present, not the type of resistors that I trained. Because I trained those discrete resistors, not the SMDs.
But I know that YOLO is not good for small objects.
Definitely. But I also tried to work on, there's another version of this application which And I try to detect also cars, objects, persons, well, from the traffic, and it works much faster. Also because I was running not on this kind of tool, but on a much powerful server. But it is able to detect very well other kind of stuff. So it depends on the training, what you want to train, and what you want to detect, what you want to recognize.
Did you explain where you trained the?
Yes, yes, I also explained. Yes, on the server. Okay, if there are no other questions, I would like to show you another demo, small, but this is a working demo. Well, this also is working, but the other one is interactive, more interactive. So I can close this. It takes a while to transfer everything there. Okay, so let me disconnect. That's good. So what I'm doing now is, let me okay. This one is another. I have enough power, enough battery. Yeah, that's enough. Should be enough. Okay. This is on Jupyter. Jupyter Notebook. This demo is an application that we've been developing for a customer, in which we had to detect, well, it was an inventory management. They had the problem. They used to analyze their own data set of more than 100,000 components every 6 months in order to establish whether some components had to be taken has to be taken in stock or ordered on demand, because many components were also much expensive, more expensive than we can think. And so having them in stock, it was a problem also, not only for buying, but also for storage, because they were big, they used a lot of space. They were a producer of electrical generators, so turbines, so very huge objects. So in this case, I have
What is order on demand?
On demand means that, okay, a component can be kept in stock. This is make to stock, MTS, means that I need these components very frequently, so I do not want to waste time in order to attend for delivery from my suppliers. So what I do is I buy a certain quantity of components, and anytime I go lower than a certain threshold, I order new components, new items. The other one is make to order. So means that I do not want to keep this stuff in my storage, in my warehouse, because it is too expensive. It is too big. There's a lot of problems in keeping this as supply. And so as long as we have a new order that requires this component, we order this. And so this became, this is my idea of on demand, okay? So we had more than 100,000 items, and I will show you. What we were told is that there's kind of an empirical rule that they use. So if a certain item is ordered more than 50 times in a elapsed time of 18 months, they keep it in stock. If it's less than that, it's ordered on demand. So it's MTO. So based on this rule, we had to invent something to do in order to analyze this inventory and make this automatic classification, NTS, MTO, because the problem was that they used to do this every 6 months. And this task, apart from this empirical rule that was applied basically with an Excel spreadsheet, they only could achieve 80% of recognition of correct assignment, because the rest had to be done manually. some expert knew which component has to be in one or the other class. And so there was a couple of persons that used to do this every 6 months for more than 3-4 weeks. It's a very expensive task in terms of time and in terms of money, because those persons were engaged in this activity for a lot of time. So we tried to understand whether it was possible to reduce the classification time to a small set of items. And well, we started with this approach that is a semi-supervised learning. So we made some assumptions, and based on those assumptions, we could perform automatic classification. So I'm showing you how to load. Well, we load first the data set. The data set has been anonymized, and the features that we were given were only those. So we had the ground truth, whether it is MTSO means it's a ground truth, whether it is generally used as MTO or MTS for them. Part ID has been anonymized, as I said before, whether the component is active or there are some different statuses, and I'm showing you which are the statuses, and then how many times has been requested, the total count, how many items have been requested in total. What is the lead time? The lead time is the time for supplying, the cost and the base price. So if we drill into the data, we see that we have a total number of items, which is more than 95,000 items in MTO. This is from ground truth. And in those MTO items, there are 83,000 items that have been all ordering. For what regards the MTS, so the items that we want to keep in stock, we have 5,000 items to keep in stock, and only 1.4 thousand items are ordered more than 50 times. So what we did is, okay, let's take this 1.4 thousand items as a reference for training. We have for sure these items that we know that match the rule. So what we assume is that if they match the rule, their features should be representing the class. So I think that if I can use them for training and I select an equally balanced subset of items from the other class, I can train. I have a very well balanced data set, so I can train even if on a very small number of items, but the data set is balanced, so I can have a good quality in training. This is what I expect. So what we did is that in this case, we select those items. So we select those 1,444 items from the MTO. So an equal number of items from out of the 83,000 that we have in MTO. Okay. So we have a good selection, and we join the two data sets in order to have a training data set. So you see here that we have sub-selection in which we have our training data set. It's around 3,000 items, those an equal number, as I said, MTO, MTS. The rest is test, in order to see what is the accuracy and the indicators that we can achieve. So what we do here, we do some pre-processing. Okay, what about pre-processing? What we do is first, sticking to the theory, the categorical variables should be mapped into one node. in this case, I did also a test in which I didn't modify, I didn't do this one-hot mapping, but I simply replaced the categorical features with the numerical classes, numerical items, in order to feed my algorithm. But as I more or less no difference. So let's do what is theoretically correct. And there is, well, let me see if I set correctly the setup, because where is it? No, maybe it's further down, because there is also a, okay, no, here is still preprocessing in which I'm detecting, I thought it was further, okay, in this case, these are the classes: statuses, which are active, inactive, incomplete, obsolete, and planning, and MTO, MTS as the ground truth. So I replace MTO, MTS with 0 and 1 because it's easier for me. Whereas on status, I perform the one-hot conversion. In this case, there's a part ID feature which is not representative. It's just something, it's a description, so it's metadata. I do not want to bother too much about this, and so I drop the column. So I drop it, and my data set does not contain this. Well, the check of how many of those features contain any null items is just to see that we need to do something. In this case, we have many features that contain a complete list of items. For each of the item has its own value, but there are some missing values for what regards lead time, unit cost, and base price. So if I want to do something on this, well, I have no big choice, because I do not know what is the price. I do not know what is the lead time of some components. And doing some averages, doing some other stuff, guess, it's still a guess. So given that we do not know what is the correct value, we replace that with 0. So everything is replaced with 0. If it is null, it's replaced with 0. And now it's time for training the classifier. Okay, here we have some tools, some libraries, and multi-layer perception classifier, but I could test also different classifiers because I wanted to make sure that I pick the best one. And we can see what we can have. There's we see MLP classifier, decision tree, support vector classifier, random forest, and I realized that the best one was the random forest for time and for execution time and for accuracy. I scaled the data. So scaling is important because we bring all the data with the yes, unit standard deviation and average mean and zero mean, sorry. And in this case, I want to transform only the lead time, unit cost, and base price for both the data sets. So for tests and for MTO and MTS. And then we use k-fold cross-validation, 10 folds, because you see that the number of folds is 10, and a training on 1,000 passes. So everything here is to set up all this stuff, and I performed the training here. You see here just a training with this. Okay, now I'm performing the training. You see this is running, and for each of them we have intermediate values of precision, recall, F1, all the scores. And you see that when we get to the end, our average accuracy is 97.9%, which is pretty good because in this case we have 99. F1 is 81%, precision 97, recall is 74. So here we have the, well, ROC analysis, and we see that well, classification is good enough, is representative. Finally, confusion matrix, which is something which is very interesting. You see that classification is correct for what regards MTO items. We still have some wrong classification with with regards to the MTS. MTS items are not completely recognized correctly, but the false positives are very few. So I think it's interesting. Yeah.
It's not balanced. So
Yes, exactly. It is not balanced. The data set is not balanced, but whereas the training has been done on a balanced data set, but it is not very well representative. I think that this was just to start. We were given very few features. The data set, their database contained a lot of additional features that we've not been given. So I think that if you have, let's say, more features in order better identify what are the discriminating characteristics of each of the items, we could improve the classification, even if 97% per se is a good result, because they have only, let's say, 2,000 items to assign manually, compared to the 20,000 they had before is 10%, which turns out to be, let's say, 1 week work, I would say.
the quantities order usually has very long tail. Some items are ordered many times, and most of the items are ordered few times.
Yes.
So when you normalize this data, is standardization a good way, or standardization after logarithm is a better way?
We can do a test and see what happens if we do not apply standardization.
No, you need more sophisticated normalization, like the standardization of the log of the quantity.
Yeah, I see. Okay. Yeah, but the problem is that we were given this data set with the number of items. So the problem is not, it's probably a problem which is not modifiable, because this is the composition of their data set, their database. So they have a lot of items which are ordered very few times, whereas a small number of items which is ordered many times. And this cannot be changed.
I know, but at least you can take it into consideration when you prepare your data. Again, for me, I think using a different normalization technique may give better results.
Possible. Maybe we can try something else in order to improve the result. Well, what I tried is I tried to scale, not scale. Do I not using? Let's say if you want to see what happens if you do not scale data, it's just a matter of false here, so it's not a problem. I start over everything, and we see what happens. Doesn't take too much. Okay, we are here. And you see the result is the same in confusion matrix. If you look at the, yeah, here. The scores are the same. Whether we scale or not, it doesn't change too much. Yes, for the random forest.
It's the same, even if you keep the data as categories or you.
Let's do.
Yeah, it's the same. Random forest.
Let's use an MLP. Yeah, this is, I think it's the best one, because we can use this classifier. Let's do something with the new classifier. It's just a matter of changing a few variables and see what happens. takes a bit more because multi-layer perception is requires a longer training. Okay, as it's going. ROC is better. You see here, okay, come on. You see the accuracy is smaller, and I think that also, yeah, there's a lot of mistake. You see. MTS is much better, yes, but we have a lot of mistakes here. Let's say we try the last one in order to scale the data. Let me try to see what happens if we scale again. Standard scaling, which is zero mean and unit variance. You see here, it improves, but still we have a lot of mistakes in MTS. And we also lose a lot on MTO here. So I think it's not so good, even in this case. You see here, let's see what's 93%. So it's a good tool to do some experiments to see what happens and to check different classification algorithms with different options. Yes.
The features that you have, you don't have, you have only the read time as a time component.
Exactly.
But what about like the inter-order time, the time between the purchases of each?
That was the problem. We didn't have all the information we required because those features were important to add more meaning to the items.
Yes.
And this what was I was saying before. The number of features we were given, it's small. And that if we had access to the whole database with all the possible features, which, as far as I remember, were more than 40 different features. We have only 5 here for representative, 5 for representative features. So I think that if we get access to all those features, we can improve the classification and improve also the quality of the data set. So it takes time to do that, depends on what they want to share. I think that this is what they could share with reasonable confidence that it was not protected by, let's say, NDA. I think it's also because intellectual property needs to be protected for them. So maybe some internals didn't want to show us some internal, yes. So this is why I think this is the amount of data that we were given. But I think it's a good experience, good, also because you see, well, we could do that in a semi-supervised way. Okay, I'm done. If you do not have any other questions, yes.
This project is like you approach the company or they approach you?
Franco,
So our spin-off at the
we approach the company.
To a student of us, to the bigger company, and they proposed to us and to other possible collaborators.
This task, yeah.
This task. The end of the company was restructured.
And nobody got to the end.
Now we lost the connection.
Exactly.
Because if they approached you, then they should have been generous in giving you the clarity.
Yeah, I think that the problem is that we, as you said, there was a former student of ours that used to work for them, and we were approached in order to, as long with the other 2 or 3 companies, to try to solve this one. But as long as we completed this task, the company was restructured and nobody got the task.
When our student now is a lecturer in England.
Yes, it's a lecturer in a university in England, in UK. So it's
for us it's a success.
Absolutely.
what is like the ecosystem for collaboration in general? Academia and,
Okay, this I think it's better he replies because
is not so good because large companies try to continue to use a standard software approach. So they work like web companies. There are a few companies that create a value on can you stop the recording?
okay, I can stop the recording. Yeah.
So this is
Where is stop recording? Is it wrong? Can you do that? Would you like to do that?
This is the last session.
We're done.
Just say goodbye.
Okay. Goodbye, everyone. Thank you for attending this session. And now it's a private conversation. Is cannot be disclosed to everyone. Okay. Thank you.
The